Algebra 2, it isn't Algebra 2 standard. But we know from algebra that square root of -1 is equal to I, right? Remember that? Okay. Now, there's a lot of discussion about where that comes from. A lot of textbooks, and even this one, is going to tell you that a long time ago, people were interested in solving something like this. A very simple quadratic equation. Okay. Other papers argue that they're really the people that were discovering the need for I were solving cubic equations. Nonetheless, it's trying to solve a very simple type of problem that our real numbers don't allow for. Because think about what we're saying here is we're going to take a number, some value of x, and we're going to square it. So think about all your numbers of x, whatever you want them to be, as big as you want them to be, as small as you want them to be, negative whatever. If I square it, I get what kind of number? Positive or 0, right? If I start with 0, okay? I'm going to get a positive number. If I add 1 to it, it now is developed into a larger positive number, right? So how can I make it equal to 0? And we're asking that question. So our real number system didn't allow for that. Okay? So we developed or invented this concept, this number, I. Okay? And that allows us now. Because now if I take that, you guys know that I squared is equal to -1, correct? Okay. Well, if x is I squared would be -1. -1 plus 1 is 0, right? And now we solve that problem. So, this is a very useful idea. You know, obviously, maybe it's not extremely natural for us to think about this. And really, when the people that, long ago in like the 1500s, 1400s were developing this stuff, and writing about it, people didn't understand it either, okay? That were trying to read their work, and imaginary got tagged to this type of number, and then people think, well, they're fake numbers, they're not really existing. They do exist, and they have really good applications in things like electricity. A lot of engineering uses complex numbers, and very useful. It becomes a very applicable set of values for us. Just going back to what we talked about the second or third day of school. Remember our natural numbers, our whole numbers, our integers. The next group was our rational numbers, right? Then we had our irrational numbers, which we said the irrational numbers were your real numbers remove your rational numbers, so things like pi and square root of 2 and stuff like that. And then, if we collect our irrational numbers and our rational numbers all in a group, align them on a number line, we get our real number line, right? Our real numbers, okay? Well now, because of this creation of imaginary numbers, we have another group, we have another subgroup. But they don't belong to the real numbers, okay? So imaginary, I'm going to write pure imaginary over here. You might see this written differently depending on where you're looking, but I think this is a good way to explain this to you guys. Pure imaginary numbers would be like 1i, 2i, -2/3 I, something like that. Okay? And that's the group of numbers there. Okay? Now, if I've got a group here and a group there, let's collectively, group them together. Just like we did essentially with the real number, or with the rational numbers and the irrational numbers, right? We collected them together and said they became our real numbers. Well, when I collect my real numbers and my pure imaginary numbers, we get what we refer to as our complex numbers. And we use a capital C with a little line through it to show that. Okay? But a complex number, and you've seen this before, is anything that is written as A plus BI, where A comes from this list, comes from the real numbers, and BI comes from this one. Does that make sense? So we're going to pull a number out of these lists pull a number out of this list and put them together. Okay? So something like maybe 2 plus 3i. That's a complex number. Okay? Something like 1/2 plus pi I. It's a complex number. Okay? Now, what gets confusing for people is that a number like 5 shows up in its innermost place as a natural number, right? Well, doesn't 5 then belong to everything that's around it? Okay, 5 is natural, then it's also a whole number. If it's a whole number, it's also an integer. If it's an integer, it's also a rational number. So forth. It's a real number. Well, then it's also going to be a complex number, right? So anything like a plus bi, like that, well, that's an example of a complex number. Because what is the bi value? What is b if I write just 5? 0i? Can I do that? Okay. Did 0i come from a purely imaginary group? Yeah. Okay. Because this is basically any number you can think of, attach an I to it. Okay. But most of the time, I'm not going to ask you, is 5 a complex number? Hopefully we recognize that it is and we come to terms with that. But for the most part, we're going to say 2 plus 3i. That's a complex number. You're going to be familiar with that. You're going to recognize that being complex. Right now, we need to talk about this because we're taking square roots. We're doing that discriminant, and we're getting negative numbers under the radical. So we want to be able to reference what those mean to us and some work that we can do with them. But eventually, we're going to start talking about a concept that says no matter what type of polynomial you start with, no matter what, just starting with like x squared plus 7x minus 13 equals 0. Okay. Maybe it doesn't factor, I don't know how it factors. I guess it doesn't factor real nicely, but what we end up with is a theorem that says no matter what you start with here, no matter how big that degree is, you're going to be able to break that down as x plus or minus some quantity times x plus or minus some quantity. Okay? Every one of these sets of parentheses is going to be a binomial that is a first degree linear term. Okay, or linear expression. So for instance, if I had like x to a third here, we're going to eventually get down to a point where I can have a third one of these. Does that make sense? If this is x to the 8th, I would be able to get 8 of those things. Alright? But what happens a lot of times is that those 8 things are a collection of, they might be, let's just go back to 3 to make things easier. This one might be a 3, but this might be then 5i, and this might be negative 5i. Does that make sense? So you're going to end up with maybe real components and imaginary components as parts of those binomials. So we need to be able to talk about this stuff, realize what this I means, and hopefully a lot of it is review for you. Okay. First thing I want to know, or want you to know, is we developed, and we have square root of negative 1. We developed and said that is our I. Okay, that is the interpretation that we're going to use. Okay. So the next question then is, well, what if I take maybe I wrote this. Makes it a little bit easier to see that I equals square root of negative 1 like that. I take I is equal to square root of negative 1. Now if I square that, it looks like that, right? So what's that going to give me? If I evaluate that, it gives me negative 1, right? And that's a fact that you guys learned last year with Mr. Coles, right? I squared is equivalent to negative 1. That's part of our definition for what I is equal to. Okay. Now and usually that's really all you need to know. I'm going to go a little bit further to show you some algebra that we do occasionally with this stuff. If I wanted to go I cubed, well, isn't I cubed, can it be rewritten as a product of those two things? I squared times I to the first, is that still I cubed? Well, I squared is negative 1. And we're just going to leave, we're not going to change, once we get I, we're never going to change it back to radical negative 1. Does that make sense? The invention of I, or the discovery of I, was intended to get rid of that. So we can rewrite that. Okay? So I'm not going to ever see I and want to go back that way. Does that make sense? Okay, it's kind of a one-way street. Start here, we want to go to I. So I'm already at I, I'm not going to go back to the radical -1. Okay? Now I squared is -1, I is just I, so I get -I. So I cubed is identical to -I. Okay? That's a real nice fact to have because it's kind of a power reduction idea. If I got I cubed somewhere, dealing with a third power is pretty hard. But isn't dealing with the first power a little bit easier? So we have that rule that can allow us to depreciate that power of 3. I to the 4th, I squared times I squared. Did you hear that? Well, what was I squared? -1. So -1 times -1 is just 1. Okay? And those are really the 4 that we need. Like I said, you only really need the 2. But those are the 4 that usually a pre-calculus course will show. If you ever go beyond, and maybe some of you have some desire to go take some college courses, if you take it's called complex analysis. This is kind of one of the first things that they talk about in that course. Just analyzing the complex plane and how these numbers work and what we can do with them, that kind of stuff. Well, then we got I to the 5th. Well, I to the 5th is just I to the 4th times I, isn't it? What was I to the 4th? 1. So I get I again. I to the 6th, isn't that just I to the 4th times I squared? I to the 4th was 1, I squared was -1. I to the 7th is I to the 4th times I cubed. Well, I cubed was -I, right? I to the 4th was 1, so I get -I again. And then I to the 8th is just I to the 4th times I to the 4th. Apologize for running out of room here. But what's I to the 4th times I to the 4th? Just 1, right? Is this list right here, I, -1, I, the same as that list there? I, -1, I, 1. Okay? So what we get is what we call a cyclical group there, where if I give you I to the 9th, you know that the cycle starts over and you jump back up to I. I to the 9th, same thing as I. I to the 10th, jump back up, it's the same as I to the 6th. I to the 6th was the same thing as I squared, so it's -1. Does that kind of make sense? The reason I say you only need I and I squared is if you understand your exponents well enough, hopefully we do, I've got I to the 30th. I don't want to have to write that list out 30 times, right? Okay? And we could do maybe some division by 4 to that number and look at the remainder. And the remainder would tell me which one of these to choose. This is the way I think most people feel comfortable with this. Can I rewrite this as I squared to the 15th power? Is that still I to the 30th? Well, what's I squared? -1, right? Now, -1 multiplied by itself 15 times should give me what? -1. So if I were to write that list out, I squared, I to the 3rd, I to the 4th, I to the 5th, I to the 6th, I to the 7th, all the way to 30, I want to find out that I to the 30 jumps back to give me -1. Okay? Every single one, everything you can do. Now, it's really easy with even numbers. This is always I squared, and then that factor that goes with 2 for that number. So the factor that goes with 2 is 15 here, right? So I go I to the 40th, okay, I to the 22nd, something like that. Those are easy to do. But if I have I to the, let's say, 47th, okay? You want to do it a little bit differently. This way, because it's odd, right? 47 doesn't evenly divide by 2. So if it doesn't evenly divide by 2, I can't write it as a power of 2 very easily. Okay? So this is what you do. You rewrite it as I to the 1st times I to the 46th. Is that still I to the 47th? That makes sense to everybody? Now, this I to the 1st is just going to be I. But I to the 46th, can I rewrite that as I squared to the 23rd? That makes sense? 2 times 23 gives me 46, right? Okay? So basically, if I get an odd exponent here, I just break it down so that I have I to the 1st times an even exponent. Okay? Now, I squared was what? Negative 1. If you raise that to the 23rd power, if I take negative 1 and multiply it by itself 23 times, what do I get back? Negative 1. So it gives me I times negative 1, which is just negative I, right? Okay. And that's just kind of an exercise that a lot of times they ask you to kind of work with just to get in the groove of dealing with I and I squared, that kind of stuff. It's just a neat feature about those terms. Okay. What the PowerPoint gets into is showing us some operations that we can do with complex numbers. And they're not anything that you have not seen before. Okay? So the first couple kind of walk you through the idea and the concept of why we want to have this I and what question we were trying to answer. So we talked about that already. And then they get into the idea of telling us what A plus BI looks like and how that develops our complex number system. What I want you guys to know from this slide is if I have something like A plus BI, okay, this number comes from your real numbers. That comes from that group of real numbers for your number line. Okay, your real number line. This here comes from your imaginary list. Okay? And then when we add or subtract them together, we get that complex number. Okay? So they're going to ask you what's the real part and what's the imaginary part. Well, the real part is the real number part. Okay? The imaginary part is the part that has I with it. Okay? Also, it's important to realize that when we see a theorem or something like that, or a definition throughout the year, and it says X belongs to the real numbers, well then that theorem, whatever is presented in that theorem, does not work for complex numbers. Does that make sense? Because if it worked for complex numbers, it would say X is an element of the complex numbers, and then everything that we're doing would work with things like A plus BI and stuff like that. Okay. So it's very important that we understand those things. A lot of people glaze over those facts when we see a theorem that, hey, it only works with these numbers. They just kind of don't pay attention to it. But it is something that we really want to focus on and understand, because it can get us in trouble if we don't do that. So they're going to ask you, can you go through, and I've already moved these away, but 3 plus 4i, if I look at 3, that's my real part. Okay? It does not have an I with it, right? 4 is the imaginary part. Is that pretty easy? Just recognition. And you're going to see some questions in your homework like that. I think the WebAssign is going to want just the 4 when you ask for the imaginary part. If you write 4i, like on a test by paper, I don't care, that's fine. But they just want the coefficient. 1/2 is the real part. 2/3 is the imaginary. Down here, you just got to be careful because they're not showing the plus 0. Okay? So 0 would be the real part, and then the 6 is going to be the imaginary. And then likewise, I think the one on the bottom is the hardest for people to recognize. Just not used to it. Okay? But -7 can be written as -7 plus 0i. Doesn't make a whole lot of sense right now for us to do that, but -7 would be the real part, and 0 would be the imaginary part. Okay. Kind of working through our operation. We'll do an example or a couple examples of each of these. We've got enough time here. The first one is how we add these things. Add and subtract. What is nice is that if you can add these, you should be able to subtract them. And if you can multiply them, you ought to be able to divide them. Okay? So adding and subtracting, just general format, says if I have two complex numbers, A plus BI, plus then C plus DI, if I have those two things, and I want to add them together, all you have to do is locate the real parts, okay, and do that operation between them. So A plus C. We'll do that. Okay. Then you locate your imaginary parts, and you're going to add those together. So plus BI plus DI is usually the way it looks initially. But what do they both have in common? I. So we write it this way. Factor that I out. We get B plus D. Okay? And that's just basically saying the imaginary parts are like terms, right? you can add the coefficients of those like terms. The real parts are like terms. Just add those quantities. Okay? So we add real part to real part, imaginary part to imaginary part. Okay? That's kind of just the general rule for this. So if I start with, like 2 plus 6i plus then 5 minus 3i. Okay? Real parts are 2 and 5, right? So I'm going to add 2 and 5 together, and it gives me 7. The imaginary parts are 6 and negative 3. Well, 6 plus negative 3 gives me 3, right? So 7 plus 3i is the sum of those two things. Okay? All you got to do is add those two parts, and then add those two parts. And you got one concise complex number. I'm not 100% sure. I'm not really good at electricity. One thing I'm really good with electricity is getting shocked. Seems like every time I do something at home, I shock myself and then start sweating for about 3 hours. But complex numbers, with electricity, you got your current and your resistance, right? Okay, resistance is the idea that something is slowing those electrons down eventually. Okay. So if I have like a 9-volt battery and a 10-foot cord, that cord is so long, there's so much material resistance in that cord that my electrons from my 9-volt battery are not going to get to the end of that cord. Does that make sense? Okay. So it wouldn't power anything at the end of that cord. So I'd have to have a bigger battery, so the more electrons, and they can flow faster, that kind of stuff. But what we do is with complex numbers is we have the idea of like current and resistance, and we can measure maybe one battery or one piece of cord with one number like this, where maybe the 2 represents one of those features, current, and maybe the 6i represents the other feature, resistance. Does that make sense? And now if I add those two together, that idea would be maybe I've got now 2 cords. Okay? And when I add those collectively, those 2 cords together, 2 power cords, collectively now they have a new resistance and a new current. Does that kind of make sense? All right, so that's kind of the reason why we have these numbers and where we can use them, is that they turn out to basically represent one idea, but 2 quantities from that one idea, and that's really nice. I hate doing stuff like this because I don't know. I could be totally wrong that it's current and resistance. I know it has something to do with resistance. But I hate doing problems like this because you don't necessarily see right away an applicable real-life use for it, right? But that is one of the main places that we use complex numbers. And they don't use I in the electrical field because I stands for current. They use J as the complex number. Not a big deal. But if I want to subtract these two things, like minus 7i minus 5 plus 4i, some arbitrary values here. Again, I just go 2 minus 5. Well, 2 minus 5 is negative 3. And then just be careful here because you got to take the negative here. So negative 7 minus 4. Negative 7 minus 4, negative 11. So negative 3 minus 11. Pretty easy. All right. Inevitably, everybody finds out at some point you can use your calculator to do a lot of this. Okay. So I'm not going to show you how to do it, unless you guys kind of figure that out on your own. But a lot of this stuff is doable on your calculator if you want to kind of verify things. So that's addition and subtraction. It's really nothing mind-boggling, I don't think. Okay. Multiplication and division. Okay? If I have A plus BI and C plus DI, that's how we're going to see multiplication of 2 complex numbers. Well, that's a binomial times a binomial, right? When you take a binomial times a binomial, what is the procedure that you use? Yeah, you FOIL. Okay? So all we're going to do here is we're going to say that that is equal to A times C, A times DI, BI times C, okay, and then BI times DI, okay, something like that, every single time, okay, and it's just FOIL. All right, so if you don't want to write that down, just remind yourself somewhere that you're going to FOIL. Now what's nice here, what does I squared always turn into? -1, right? So I've got a coefficient here times a I squared, but the I squared is going to become -1. So this turns into just a constant, right? That is just a constant, right? What can I do with those? Combine them. They're like terms. What are these two things? What are they? Both have I on them, right? They're both imaginary numbers, right? Pure imaginary numbers. They're like terms. Combine them. Okay? So that's kind of the goal here when we do a problem like 2 plus 5i, -3 plus 6i. Okay? FOIL, remember FOIL is just a distributive property multiple times. I'm going to take 2, I'm going to distribute to this stuff. So 2 times -3 gives me -6, right? And then 2 times 6i gives me 12i. And now I'm going to distribute the 5. 5i times -3, -15i. And now 5i times 6i gives me a positive 30i squared. Okay? Now this is how I do it. So you develop a technique that's good for you and that makes sense to you, whether you have to rewrite this whole line again. I don't like to rewrite that whole line. So what I always do is I say, well, I got I squared here, right? Well, I squared turns into what? -1. So I can change that. Awesome, marker. Change that to a -1. Well, what's 30 times -1? -30. So the way I do this, okay, so we start off with positive 30i squared, right? I just always write a slash through that and come back over here and change that sign. Okay? I think it's just a shortcut that I use, that I understand, and that I'm familiar with and comfortable with. If you have to rewrite the whole line, rewrite the whole line. Okay? So now, that -6 and that -30 are like terms, right? So what's -6 minus 30? -36. 12i minus 15i.
Pardon the interruption. A few announcements here. Anyone in Mr. Gomez's classes need to report to study hall for the remainder of the day unless you hear otherwise. You will eat B lunch. Again, anyone in Mr. Gomez's classes will need to report to study hall for the remainder of the day and eat B lunch. Mr. Wilkerson's classes can now report to his room for the rest of the day. Again, that's Mr. Wilkerson's classes can now report to his room for the remainder of the day instead of study hall. And lastly, if Paige Williams could please come to the office.
Okay,
Thank you.
real quick, division is no different than multiplication. Okay? But you have to know what you're going to multiply by. If I have a denominator of 5 plus 4, does anybody remember from last year what I multiplied by here? Multiply by the conjugate. I'll put a video together of doing an example like this from the website. There is homework. It'll show up next period, but it's not due tomorrow. Okay? Get a start on it. You can ask questions about it, but we'll continue to talk about this stuff a little bit tomorrow.
I have to pee really bad. Are you going straight to early? I'm glad you said that on freaking love.
All about buckets. Yes, sir.
Jared, are you a fan of basketball? Yes, sir.
Yes, that's done. Yeah, email me.
Are you conducive
I'll
Thank you.
Yep. Let me know if that ever happens again.